Good evening. Today I will be presenting our work title Optimizing Diabetes Prediction Using Ensemble Learning Techniques for Enhanced Accuracy. The of this research was to build a more accurate and reliable machine learning model for early diabetes prediction using real clinical data from over 5,400 patients in the DiaHealth dataset. Slide 2. Background and motivation. Diabetes is a major global health issue. Right now, about 589 million adults live with it, and by 2050, that number is expected to reach 853 million. What makes it more concerning is that over 40% of people with diabetes don't know they have it until complications appear. Although machine learning is often used for prediction, many models struggle with imbalanced data, nonlinear relationships, and poor generalization across different populations. This created the motivation for our work to develop a more accurate, robust, and clinically useful prediction model. Slide 3. Objections and contribution. Our objectives were increase accuracy and recall, so we identify diabetic patients more reliably. Build a model that generalizes well across diverse clinical conditions. To achieve this, we introduced a stacked ensemble model using XGBoost, LightGBM, and CatBoost as base learners combined through a logistic regression meta learner. We also use SMOT to fix class imbalance and thoroughly compared our model to traditional algorithms like naive Bayes, decision trees, SBM, and random forest. Slide 4. Dataset and pre-processing. We used the DiaHealth dataset from Bangladesh with 5,437 patient records and 13 health features including glucose, BMI, blood pressure, age, weight, and medical history. Our pre-processing included removing redundant features, inputting missing values, standard scaling, and 80 by 20 stratified split. Smart oversampling to increase minority diabetic cases. Feature scoring using select K based, which confirmed all features were relevant. This produced a clean, balanced dataset for modeling training. Slide 5. Baseline models. We elevated several common models, naive Bayes, decision tree, SPM, random forest, to simple ensemble variation. These models perform reasonably well, but is had limitations like naive Bayes independence assumptions or decision trees tendency to overfit. This gave us a solid baseline to beat. Slide 6. Proposed stacking model. Our main contribution is a stacking ensemble combining XGBoost, LightGBM, CatBoost. The outputs of these models are then fed into a logistic regression meta-learner which learns how to weight their predictions. We trained the ensemble using five-fold validation, smart balanced data, turn hyperparameters. This idea is simple. Different models capture different patterns and stacking blends their strengths into a more reliable prediction. Slide 7. Performance comparison. Here are the key results. Naive Bayes 97.7% accuracy. Decision tree 98.25%. SBM 99.08%. Random forest 99.36%. But our proposed ensemble list 99.3% accuracy, 0.95 F1 score, and 0.99 recall. The near perfect recall is especially important because it means the model rarely misses diabetic cases, which is critical in a medical setting. Slide 8. Key results. The confusion matrix highlights how reliable the model is. Correctly classified 1013 of 1009 non-diabetic cases. Correctly classified 68 of 69 diabetic cases. The precision recall curve also performed very strongly with an average precision of 0.980. Overall, the model shows highly consistent performance across all measured metrics. Slide 9. Comparison with related work. We compared our results with previous research. Earlier boosting models achieved around 90 to 93% accuracy. Other ensemble studies ranged between 90% and 99% depending on data sets. Our model achieved 99.36%, slightly outperforming recent work and showing stronger generalization on a larger clinical dataset. This positions our approach as one of the more accurate and reliable models in current database prediction research. Slide 10. Future work. In summary, we developed a stacked ensemble combining three powerful boosting models with logistic regression. On a real clinical dataset, our model achieved high accuracy, high recall, and excellent overall reliability. This makes it promising tool for early diabetes screening and clinical decision support. For future work, we plan to add explainable AI such as SHARP to improve transparency, incorporate time series data for long-term risk prediction, validate across multiple countries, build a real-time clinical tool. Thank you very much for listening.